If we want to model a sequence of numbers, A1, A2, A3, and so forth, some sequence, then we can first of all look at the ratio sequence. If the ratio sequence, A2 over A1, A3 over A2, and so forth, of members of the sequence divided by their predecessors is constant, then we know that we can model the sequence by the function a of n equals a times that constant to the n. If we know what this constant is, that constant is going to be our growth factor. Okay? Now, if the nth difference of a sequence is constant and not equal to 0, then an is a degree n polynomial of degree n. And if we put data pairs like 1A1, 2A2, 3A3, 4A4 as pairs of data points, we can use an nth degree polynomial and exactly fit those data points to obtain a function a of n for the sequence. If the ratio of the first difference of the sequence is constant, then a of n is a times that constant to the n plus c, some c. And the c is what comes out of the fact that we have to do the first difference before we do the ratio. If we have a sequence generated by something like this, when we subtract the members, the c essentially subtracts off and we're left with something that we can model with an exponential. In a depth versus time context, we can have depth increasing at an increasing rate, a constant rate, or a decreasing rate. Okay? And these behaviors are illustrated by the graph in each of these cases, and that's fairly obvious. To interpret the slope of a graph, the slope is the rise of the graph divided by the run. So the slope between 2 points of a graph will be the change in whatever quantity is depicted on the y-axis per unit of whatever quantity changes on the x-axis. The rise will be the change in the quantity on the y-axis. The run will be the change of the quantity on the x-axis. So that when we divide rise by run, we get the rate of change of this quantity with respect to x. And again, that rate of change is the change in the q quantity per unit of x quantity. And that's what we're talking about here.